In this section, we're going to look in more detail at how moving charges can create magnetic fields. We'll use a law called the Biot-Savart law, which tells us the magnetic field created by a single moving charged particle. Now, it's a little bit more complicated than the magnetic field due to a wire formula. So let's go over each of the different parts. The Biot-Savart law says the magnetic field due to a moving point charge will be given by mu times the q, which is the charge of the moving particle. V will be the velocity of the particle. We'll cross the velocity vector with a directional unit vector, r hat. And I'll go over how to find r hat here in a minute. And then we'll divide by 4 pi times the distance squared, where the distance r is going to be the radial distance from the charge creating the field to the point where we're evaluating the field. Let's see if we can use this law to find the magnitude and direction of a magnetic field at the given points due to a moving proton. And it's moving with 100,000 meters per second, so a high speed. Point A is 1 centimeter away from the proton in the negative x direction. So let's start with point A. We want to find the magnetic field at that point. Now, we had said before that the magnetic field around current-carrying wires would be concentric circles. The same kind of thing is going to happen around a moving point charge. So if we draw a circle here, in 3 dimensions, of course, then this would be a magnetic field line. And we just have to use the right-hand corkscrew rule to figure out what the direction of that magnetic field will be. Now we can see that our particle is moving in the positive y direction right now according to the given coordinate system. So we want to go ahead and point our thumb in the direction of motion of the positive charge. Then simply imagine wrapping your hand around that y-axis right now. Okay, as we can see, the fingers are definitely curling in a clockwise fashion here around the y-axis. So that's going to be the direction of our magnetic field as well. Okay, so this is one way to determine what the direction of the magnetic field at point A will be. It's clearly going to be coming out of the plane here, and this plane is the XY plane. We can see that. So that means that our magnetic field is going to be pointing up at point A. Alright, so that's going to be the magnetic field vector that we're looking for. Alright, now the great thing about the Biot-Savart law here, though, is it doesn't just tell us the magnitude. It will tell us the direction as well. Now, it may be that we don't even need the direction. If we don't need the direction because we had already found it using the right-hand corkscrew rule, then we can modify it a little bit. And we can just look for the magnitude. Alright, so the magnitude will be B equals mu Q. And then we have the cross product of V crossed with R hat. We've seen in the past that a cross product can be given by the magnitude of the first vector times the magnitude of the second vector involved, and then times the sine of the theta between them. And then we'll divide by 4 pi r squared. Now r hat is a unit vector. This means its magnitude is just 1. All right, so let's simplify it even farther. All right, so let's find B at point A. We'll have 4 pi times 10 to the minus 7. We need the charge of a proton. We need its speed as well. And then we need a sine of an angle. But what angle do we use? Well, now we have to draw the radial vector. The radial vector points from the charge to the point where we're evaluating the field. And this would be R for point A. Notice that it is 90 degrees to the velocity vector. And so that's the angle that actually goes here. Notice that sine of 90 will be 1. So we're going to get the full magnitude of the magnetic field in this case. Okay, now we'll divide by 4 pi times the distance from the charge to point A, which is 0.01 meters. And it's done. Now we'll plug it into calculator. 1.6 times 10 to the minus 17 teslas. All right, now if we wish to use our corkscrew rule to tell us the direction, then we can just put a vector over its head. And I'll use vector notation now. The magnetic field at that point is in the positive k hat direction. All right, now what if we want to use the full right-hand rule for cross product to determine the direction? Then how would we do that? It's just a little bit different way of finding the direction than this corkscrew rule here. What it says is you want to take your velocity and then cross that with r hat. And r hat, of course, points in the same direction as r. Now the right-hand cross product rule, when used on these two directions, will give us a new direction, and we want to figure out what that direction is. So take your pointer finger and point it in the direction of V. Okay, because that is the first vector given. Then we need our middle finger to point in the direction of R. The result will reveal that the thumb points up. So this is the direction of V. This is the direction of R. And the result points up. in the direction of our magnetic field. We get the same result doing it this way as we had using the other right-hand rule. All right, now we can answer the other questions, and some of them will actually be fairly easy to answer by symmetry. We see that point B is the same distance away from the moving charge. And so the magnetic field there is going to be the same strength, but in a different direction. So the magnetic field at point B ends up being 1.6 times 10 to the minus 17 teslas. And this is going to be in the negative K direction. We can answer D in a similar way. D is also 1 centimeter away from the moving charge. Therefore, the magnetic field at point D will be 1.6 times 10 to the negative 17 teslas. And this time it looks like our vector is going to be pointing in the x direction, which is the I hat direction. However, when we do C, we see that it is actually twice as far away from the charge as A is. So for the magnetic field at C, what we're going to find is that it's actually weaker. Let's go ahead and plug in the numbers for that. We'll need 4 pi e to the minus 7, 1.6, e minus 19, same speed of the proton, same angle between the velocity and the radial vector. And we'll divide by 4 pi times 0.02 squared. That's the only change, actually, is just the distance from the proton. And let's see how much the magnetic field is affected here. I get 0.4 times 10 to the minus 17 teslas. So it is 1/4 of the field, because it's twice as far away, and our direction will be, of course, k hat. So that is 4 times 10 to the minus 18 teslas, k hat.